So far this term, we've been talking about derivatives. Today, we're going to talk about antiderivatives. Antiderivatives, as the name suggests, is what undoes a derivative. So an antiderivative of a function f is a function where when we take the derivative of it, we get f. The indefinite integral of f is the set of all antiderivatives, and its notation looks like this, where we've got this sort of stretched out s here and a dx here. Now, you'll notice that I said an antiderivative, and the indefinite integral is the set of all antiderivatives. So this suggests that we can have more than one antiderivative to a function. So let's see what that looks like in an example. So we want to find three different antiderivatives of 3x squared. So let's think about this. An antiderivative says, what function, when I take the derivative of it, will give me 3x squared? Well, our initial reaction might be x cubed. If I take the derivative of x cubed, I would get 3x squared, which is what we want. Wonderful. So here's an antiderivative. What could another one be? Well, if I said x cubed plus 1, that would also give me 3x squared as the derivative, because the derivative of x cubed is 3x squared, and the derivative of a constant is 0. So that just goes away. And perhaps now you have lots of ideas of what our third one can be. Let's say we have x cubed minus 5. That's also going to be an antiderivative. And in fact, I could put any constant here I want because the derivative of a constant is 0. This means that I have infinitely many antiderivatives of 3x squared. So if I want to find the indefinite integral of this, the indefinite integral of 3x squared dx is going to equal to x cubed plus whatever constant we want to put on there. So I'm just going to have a c there to tell me that's the constant that I want. So in general, we can do this with any function. Our set of antiderivatives is going to always be different from each other just by a constant. So for instance, if I look at the integral of, let's say, f of x dx, then this is going to always equal an antiderivative of that plus a constant. So this capital F of x, this is any antiderivative that we want. This could be literally any of them. So for instance, here I put x cubed plus c, but I could also have put x cubed plus 1 plus c, or x cubed minus 5 plus c. I can put any antiderivative there I want. Why are these the same? Because c is just a placeholder saying that this is just a constant. So 1 plus c is also still just a constant. So these two are just the same. So again, this capital C here, this is a placeholder that says any number we want. It's not a fixed number, it's whatever we want to put there. One more thing that I want you to pay attention to here is this dx. This dx is really important to have in our integral. What the dx does is it tells us what our variable that we're interested in is. Now here, this might seem very obvious that what we're interested in is x, because that's all that is there. But as we get into higher levels of calculus, you'll start seeing more variables, and it'll be really important to establish which variable we're actually interested in. Think of it in terms of when we did implicit differentiation. Anytime that we were taking the derivative of a variable that wasn't the variable we were interested in, we had to stick, for instance, a dy dx at the end. Similarly, when we were doing related rates, we were interested in t as our variable. So anytime we took the derivative of another variable, we'd have to put, for instance, a dx dt afterwards. We'd have to indicate that we had sort of the secret chain rule. So again, what all this is saying is that it's really important to pay attention to what our variable is that we care about, and that's what this dx does, is it's telling us I'm caring about x. Now, we were saying that antiderivatives undo derivatives. And similarly, taking the derivative undoes doing the antiderivative. So differentiation undoes antidifferentiation. What this means is if I have this d dx, it's just going to undo the integral. So d dx of this integral just gives me the function right back again. Let's take a look of an example of that. So let's say we have this, the derivative of this integral. What is this answer? Well, we already know from what we just said that the derivative of this integral, these two will undo each other. So we should just get cosine of x plus x. But let's double check and make sure that's actually true. So let's start with our antiderivative. So let's start with cosine of x. What function, when we take the derivative, gives us cosine? Well, the derivative of sine is cosine, so this should be sine of x. Now what function, when we take the derivative, gives us x as our derivative? Well, if we think about the power rule, right, x squared will, when we take the derivative of that, will go down to x. But let's think about what happens when we take the derivative of x squared. This gives us 2x, right? We take our power and bring it down. But I don't want 2 in front of my x, right? I have a sort of secret 1 coefficient there. So how do I make sure that I don't have a 2 there? Well, what undoes 2? 1/2. So if I put a 1/2 in front, now when I take the derivative, I bring that power of 2 down. That cancels with the 1/2, leaving me with just my coefficient of 1 that I actually want. So that's the antiderivative of x. And then of course we need to add on a constant. So this is our antiderivative of cosine of x plus x. Now let's go ahead and take the derivative of that. The derivative of that, what's the derivative of sine? It's cosine. What's the derivative of 1/2 x squared? Well, I'll bring the 2 out front. That cancels with the 1/2. And then I subtract 1 from the power, so that gives me x to the 1. And then what's the derivative of a constant? The derivative of a constant is always 0. So that just goes away. All right, so we did in fact get cosine of x plus x back again. So the derivative does in fact undo the antiderivative. Now, we might not want that constant there. And in fact, if we're given the derivative and we have one value of the function that we know, we can narrow down from the infinitely many antiderivatives, we can narrow down to just one. You can think of this value, this f of a equals b, as an anchor point. Just like when we were curve sketching and we wanted to find some anchor points to tell where along the y-axis our function actually was, this is going to give us an anchor point to tell what our constant is. So let's go ahead and give it a try. Let's say we want to find this function where we know the derivative and we have an anchor point. What's the first thing we do? Well, we want to go ahead and take the indefinite integral of our derivative to figure out more or less what the function is. So what is the antiderivative of x cubed plus 7? Well, again, if we're looking at our power rule, this should come from x to the 4th, right? Because when we take the derivative of power, the power goes down 1, so that would give us x cubed. But again, our coefficient is running us into problems because when we take the derivative of x to the 4th, we'll pop that 4 down in front, but I don't want a 4 there, I want a 1 there. So what that means is we should have a 1/4 out front. So when I pop the 4 down, that cancels with the 1/4, and that would just leave me with 1x cubed, not 4x cubed. All right, and then the antiderivative of 7 would be 7x. And again, if we take the derivative of 7x, we're just left with 7. Excellent. Plus some constant c, and this equals our f of x. Okay, now we want to use our anchor point to help us figure out what that constant is. So we know that 3 equals f of 2. So let's go ahead and plug 2 into our function that we just found. So we've got 1/4 times 2 to the 4th plus 7 times 2 plus our constant. And so let's see, 1/4 times 2 to the 4th is 4 plus 14 plus our constant. So now we just have numbers and the constant, so we can isolate our constant to solve for it by subtracting 18 from both sides. So that gives us that our constant is -15. So now I know exactly what this function is. I figured out my constant. This is going to be 1/4 x to the 4th plus 7x minus 15. So here's my actual function. All right, to wrap things up, let's just take a look at a couple of common integral rules. So here are some sort of shortcuts that you can use to find the integral. So our first one tells us that we can pull a constant out from the integral. This is just like when we were doing the derivative. We could sort of ignore the coefficient or sort of put it on hold as we did the derivative. Similarly, if we want to take the integral of a sum of functions, we can take one integral at a time. And you'll notice that we've been doing that this whole video. And most of the rest of these are just putting into words what we already know. So for example, the integral of cosine equals sine. We know this because we know that sine, the derivative of sine is cosine. So we're just undoing what we did before. One thing that I want to pay special attention to is this, the inverse of the power rule. So the antiderivative of the power rule. We were just doing this, right? We said, okay, if we want the integral of x to the n, where does that come from? Well, we're going to need one higher power, right? Because when we take the derivative of one higher power, that'll pop us down to n. But if we just had x to the n plus 1, when you take the derivative, you pop that n plus 1 down to the front, and you would end up with n plus 1 as a coefficient, not our invisible 1. So that's why we want the 1 over n plus 1 in front, so that it'll cancel with the n plus 1 when we bring it down. Okay, so to recap, antiderivatives undo derivatives, and an integral is just the set of all the antiderivatives. So basically, when you're trying to find the integral, you just think to yourself, what function, when I take the derivative of this, will give me this function? And what is important, we want to make sure that we have this plus c at the end so that we know that I can put any constant in there and I'll still get the same derivative. And we also want to make sure that we always have this dx when we're writing our integral.